Science is truly fascinating. Deals with the study of cosmos, exploration, a lot of research, and most importantly, the study of human life. However, let us not forget physics, both quantum and atomic. With all these various topics, what happens when we misinterpret them?
Run.
Okay, what happened there was a misinterpretation of one of the consequences of Einstein's special theory of relativity, which is the length contraction. She wanted to make the ruler shorter by running as fast as she can, but the concept of length contraction does not work that way. In order to perceive something to be shorter, it has to be moving at a constant velocity relative to you near the speed of light. Einstein's special relativity was a huge step in physics, and even though time dilation seems like the weirdest thing you've ever heard, there's plenty more to get through in this theory. As it happens, it is not just time that is relative, it's length as well. And as we will find out, the math tells us that when you approach the speed of light, your measurement in space changes just like time. This is because if an observer on Earth and an observer in vast spaceship register different spans of time for an event, they must also be recording different distances, since both observers agree on the same velocity between them. Specifically, the faster you go, the smaller the object seems to be, and the shorter the distances you perceive themselves to be traveling. This is a phenomenon called length contraction.
Ever driven on a road that it seems like it goes on forever? If you look ahead, you might say you have at least 10 kilometers left to go. Another traveler might say that the road ahead seems like 15 kilometers long. If you both measure the road, however, you would agree traveling at everyday speeds, the distance you would measure would be the same.
In 1905, German Swiss American physicist Albert Einstein combined the idea that experiments performed at a constant speed will give the same results as experiments that are stationary, with the idea given that the speed of light will remain constant from both perspectives.
After simultaneity and time dilation, the third consequence of a special relativity is a length contraction. Einstein showed that an object will appear to be smaller to its direction of motion if we measure it while moving relative to us than it is stationary.
One of the peculiar aspects of Einstein's special theory of relativity is that the length of the moving object with relativistic speed would undergo contraction along the dimension of action. The observer at rest would observe the moving object, to be shorter in length.
The object is actually contracted in length as seen from the stationary reference frame. The amount of contraction is dependent upon the object speed relative to the observer.
The length that you measure when we are stationary with respect to an object is called proper length or rest length. This is also invariant. The length that we measure if the object is moving with respect to us is called relativistic length.
For example, consider a 10 centimeter stick. If this stick is traveling past you at a speed close to the speed of light, its length will no longer agree to be 10 centimeters. The length measured with the stick
motion close to the speed of light will always be less than the proper length. Now, the effect of line contraction can only be observed when the stick is moving really fast, close to the speed of light. Thus, in principle, when the stick is in motion is equal to the speed of light, then the stick should have no length.
Interestingly, while time expands from the perspective of the stationary observer, space contracts from the perspective of the moving observer. This phenomenon is also known as Lorentz contraction.
The Lorentz transformation was originally the result of attempts by Lorentz and others to explain the observed properties of light propagating in what was presumed to be a luminiferous ether. Albert Einstein later reinterpreted the transformation to be a statement about nature of both time and space, and he independently derived the transformation from his postulates of special relativity.